Okay, we're in section 36 of the notes. Again, this should be pretty much standard procedure at this point. There's going to be contents. We do expect you to read through the contents to understand the examples. I'll certainly go over those examples. When I do the examples, I'll do it in what I would consider the way to do it. Certainly, I'm not saying my way is any better than Wells's, and there's certainly a great deal of similarities between the two. Your goal is to get to the exercises, though, all right? So this document is a PDF document. It's being prepared for, the prison mathematics project participants only, all right? At some point in the future, I do plan to publish this. So if for whatever reason you need to reach out to me, and again, my name is Ron Bannon. This is a draft version of my adaptation of Webster Wells's Advanced Course in Algebra that's back to 1904. My email address is Bannon, that's B as in boy, the @ symbol, NNON.US. All right? So again, the expectation is you read. What are you reading? You're reading about indeterminate forms. All right? Now, granted, you could read through that. I'm hoping you do. You're not going to understand everything you've read, but you do read. That's what the bottom line is. You're not going to understand everything you read. No one does. No one understands completely what they've read. All right? To interpret that is going to take a considerable amount of effort on your part. All right? I guess I should talk a little bit about notation, though, and what Wells is using as notation. I just want to point out it's no longer used anymore, and I'll point this out to you. This dot above the equal sign, it's not being used anymore. All right? I'll go over the notation. I would prefer that you use a more modern notation. I'm not sure why that notation was used, by the way, but it was used at one time. All right? It's no longer used in that context. All right? So you'll see this over here. And again, I'll talk about it a little bit later. You'll see it a lot. That's Wells's notation. All right? My goal is to start doing the examples. All right? So as I do these things over here, my claim over here is, I'll talk through it, and my understanding of talking through things, it may not be well understood, but I'm going to still talk through it. So the first thing I see is this symbol, LIM. Hopefully by reading it, you know what they're asking you to do. They're asking you to take a limit. Now, what does this mean? We're going to let x approach a. Now, when I say approach a, I want to point out approaching the number a, and this is x, it's either going to happen from the right side or the left side. But the deal about this limit means don't touch the a. So you're not going to touch a. Don't touch. All right, what I'm going to do is, I know where x is going, I just don't know where that function is going. So I'm going to factor it, and that's going to be x minus a, x plus a, that's the top. I'm going to factor the bottom. That's going to be x times x minus a. Well, the deal about this is if x is not going to touch a, what do I know? I'll tell you what I know. If x is not touching a, this thing, sorry about that. This thing here would never equal 0. And this thing here would never equal 0. The only way for that to occur is if x is equal to a. Well, what does this say? It says get close to a, but you're not touching it. So there's one thing I know about this. I know that this thing is not 0. So we're going to cancel it off. And let me write this down now. Equals the limit as x gets close to a. The way we read that is a limit as x approaches a. And what do I get on top? X plus a over x. Now this is where my thought process is going to come in. I'm looking at this thing, and if x is getting close to a, I'm going to say this thing over here is getting really close to 2a. And this thing over here is getting really close to a. So what am I saying? 2a over a, which is the number 2. All right? So that limit is equal to 2. All right? This is not a very precise treatment of limits, but we're still getting a feel for it. Now let's do the next one. A little more difficult. I have recommendations for this. And what does it say? It says x is going towards infinity. What does that mean? It's getting arbitrarily large. Our recommendation, and this is a recommendation I think most math teachers would follow, when you're going towards the infinity, what you're going to do for this rational expression is to divide both the top and the bottom by the highest degree variable. What's the highest degree variable in this case? Just the x. Let me write this down. Limit x approaches an incredibly large number. We're going to divide every term on top by x. What do you get? 1 over x plus 2. What do you get on bottom? 3 over x plus 5. Again, I divided the top and the bottom by x. All right? Now, x is not 0. It's clearly a positive number. So here's the deal. You're looking at this thing, and I'm hoping you're starting to realize by looking at it, if x gets really large, this gets really small. 1 divided by a really large number gets really small. Nothing happens to the 2, though. What happens on bottom? Well, if you divide by a really large number, it would go to 0. So 3 divided by a very large number goes to 0, and nothing happens to the 5. So what am I looking at on top? 0 plus 2. What am I looking at bottom? 0 plus 5. So I'm going to say 2 over 5. All right, let's take a look at our k. And we're seeing that. All right, a little more complicated. A lot going on over here. And I'm looking at it, and it says approach the minus 2. One thing students often do is they just say, oh, you're always just plugging the number in. And the problem with that, if you did that, if you plug in the minus 2 in the first factor, you'd get 0. That's not a problem, by the way. But if you did in the second factor, you can get 1 plus 1 over 0. That's a big problem. This is the whole thing about indeterminate forms. So I'm going to erase, saying that's not a good idea, and it's not a good idea. All right? If a limit says anything, it says this. It says get close. Let me put a number line down for you. Get close to minus 2 from both the right side and the left side, but you're never going to touch it. All right, so what am I going to do over here? I want to simplify this. And someone says, no, you're making it more complicated. I don't think so. Let me write this down. Limit as x goes to minus 2. I'm going to factor x cubed plus 8. And that's something I've known from the past. That's going to be x plus 2, x squared, minus 2x plus 4, right? I just did this guy here. And now I'm going to do this one here. So how would you do that? Well, I get a common denominator. That would be x plus 2. And the numerator doesn't look too bad to me. It's going to be x plus 2 plus 1, which is x plus 3. All right? So what I'm going to claim again, we're getting close to minus 2, but we would never touch that number. So what does that mean? That means x plus 2 is never going to be 0. So what do I know about this over here? It would cancel off because it's not 0. All right, now what are we going to do? We're going to look at it and try to determine what happens. You're getting close to minus 2. And as you do that, I hope you start to realize, yeah, I get a little touchy-feely. I start to touch this thing. And over here, I want to point out if I did that, this guy here would be 4. This guy here, if I'm getting close to minus 2, by the way, I'm getting close to 4. This guy over here would get close to, let's see, minus 2 times, minus 2 would be plus 4, right? And then when you get plus 4, well, that's not so bad. So I'm going to say this whole thing gets close to 12. Now, what does this thing get close to? It would get close to 5. I'm sorry, close to 1, I'm sorry. I misspoke there. Let me get my eraser out. It would get close to 1. What's 12 times 1? 12. This can get damn close to 12. All right? Let's take a look. Mistakes happen, and I want to point that's over here. Okay? Now, a lot of work goes down there, and we're encouraging you to do the work. All right? We really do. Now, someone says you do it differently in the blue area than you did it up there. You're right. There's a lot of variations in the way to do a problem. Now, let's do this one over here. This is a typical problem. And what does it say? Get close to 1, but don't touch it. Now, when I say get close to 1, x is getting close to 1. From the left and from the right, but you're not going to touch it. Now, what could that mean? Like, if you looked at a sequence of numbers on the right side, you might say, like, 1.1. If you want to get closer, 1.01. If you want to get closer, 1.001. But this goes on forever, and we don't have forever to go on. So I'm going to erase that, and what I'm going to do is start thinking about it. So, if I get close to 1, I have divisions by 0, and that's bad news. So what I want to do is I want to manipulate this. Limit as x gets close to 1. That means get close to 1, but don't touch it. What's the common denominator here? It would be 1 minus x squared. What goes in the numerator? I'll write it down for you. It would be 1 plus x minus 2x. Again, we've done this in the past with rational expressions. going to keep going forward. And as I'm looking at that, I'm looking at limit as x goes to 1. And what do you on top? You would get 1 minus x. And what do you on the bottom? 1 minus x times 1 plus x. Okay, to get close to 1, you're not going to touch it, right? But you're getting really close to the 1 from both the left and right. What do I know? I know if I'm getting close to 1, but not touching it, I do know something. I know this factor here would never equal 0. And I know this factor here would never equal to 0. So I'm very safe in canceling it now. Again, the limit allows me to do that because it says it's not 1. If it's not 1, 1 minus x is not 0. What do you get? 1 over 1 plus x. Now again, what I'm doing, I'm thinking about getting close to 1. Well, the top is always going to be 1. There's nothing to do about that. But the bottom, when you get close to 1, it will be close to 2. So we say in the limit, that limit is equal to a half. Let's look at our k. And that's right over here. Let's keep going. No more questions. All right, so what do you do next? You're going to be doing exercises, and you got to exercise. Again, you may read Wells' section. That's fine. I'm claiming, though, that after you read that section, you may not understand completely until you start trying. But even after you start trying, I'm not going to say you have limits covered. What I'm saying is you should start thinking about what's been discussed. Right? Start thinking about it. This is a lifelong process, limits. All right? Now, when you move towards calculus, it's the centerpiece of calculus. And what's the centerpiece of calculus? The study of limits. Calculus has to do with limits. Right? So make sure you understand what's going on over here. Like for the first one, it says, the limit as x approaches 4 of this quotient. And the bottom line with the quotient, you'd have to manipulate it. And what do you know about this thing? X is getting close to 4, but it's never, ever going to touch the 4. If it's never going to touch the 4, there's some nice things about this problem over here that you can cancel off. And we go through that. Same thing for number 2. Same thing for number 3. There is a fraction error, and I realize for some students that might cause some trouble. You want to practice this, though. Number 4, again, not so bad. I bet this thing factors nicely with some cancellations. Number 5 is a fraction, but again, it's going to cancel nicely. Number 6, complex fraction. Get rid of it, move forward, and then think about it, all right? That's 2 rationals pulled together to 1 rational, go forward. Again, my gut feeling is a factorization where things are going to work out pretty nicely. This one here, again, my belief factorization, the rationals, combine it together. I mean, this over here. And I bet something's nice going to happen. It always does, all right? And then what are you going to do? My gut feeling is you want to look at SAGE. At least I hope you do. What's SAGE? It's a computer algebra system, and that's called CAS for short, C-A-S. It's free. Go to this website. You can either download the application or use the interactive web-based thing. What's this whole section about? Limits. So SAGE can do limits. It can do limits where you're approaching the number 3, like this one over here, or a limit over here where you're approaching the infinity. All right? So look over that. Again, I would say look over that not to do the problem set. You do the problem set by thinking, but realize that, SAGE has a built-in ability to do problems that are pretty simple. It has built-in functions to do problems that aren't so simple. All right, why are you learning SAGE? As you move forward in your mathematical careers, you'll have no choice but to use computer algebra system to work certain problems, all right? Not simple things, but more difficult things. Again, I want to remind you, if you find an error in my text, you should reach out to me. My email address is Bannon, that's B as in boy, NNON.US, all right? I particularly like hearing from students that find errors. Again, if you find an error and I deem it an error, and I'll always entertain whatever you say, I'll always carefully look at it. Hopefully I'm not too confused when I'm looking at what you're saying. But if I am, I'll reach out to you. If you point out an error, you're getting credit. All right, you're getting credit. Thank you. So please move forward. Before you move forward, though, make sure you're building these foundational blocks before you move forward. Thank you.